Hello everyone, I'm going to do a problem by request and it's simple harmonic motion, and this is taken from the test review, so I'm going to go ahead and get started. Now when I say simple harmonic motion, we're keeping it very simple. If for those out there in an advanced physics class or an advanced pre-cal class, you're probably going to be looking at it a little bit differently than what we have here in this example. This doesn't really model a real-world situation very well, but it gives you the basics and the fundamentals so you go into those physics classes and model it. Now in our pre-printed notes that we have here, we have the general formula, and this is the only one that we use currently at our school for our course, but it doesn't have to be that way. This represents something that, say, we're starting at something with potential energy. We're up here, we have an object up here. Now harmonic motion just means that we're going to model mathematically something that moves like in waves, just like this. And that wave will have a peak and a low, a trough, that will be consistent. It's going to bounce up and down exactly with no wind resistance, force resistance, things like that. But it's a good exercise. So here, when we have this potential energy, or raise something up, and we have a starting point here, remember cosine starts high, they model it with cosine, but it doesn't have to be that way. We can actually have a phase shift, which is pretty rare. You notice that there's no phase shift here. But we can shift it in some models, depending on time, because time is usually 0 here. But we can start low and have energy moving it up and go down like this. Okay, we could do that. That would be a sine. So we also don't have to use the physics way of doing it, like omega and time. Now this represents a formula that position is a function of time, where you have the angular frequency times time plus your vertical shift using the letter K. But I have no problem for us using something more basic that we've used in other things and just call this Bx plus C. Okay? I mean D, because C is missing. So I could have done A cosine B x plus C, or minus C, more applicable, plus D. And I could have done the same thing with sine. I just substitute sine right there. Let's go and take a look at our first example. So here we have a weight supported by a spring. It's pulled up 18 feet high. So the first thing I'm going to do is I'm going to start drawing my picture. So here we are at 18 feet. And we have time 0, so this graph is time. And this is height, or position, all right? So position is a better thing, because when you solve these functions, you're going to be looking for a position in relation to time as a function of time. It drops a minimum height of 10 feet, so it goes down to 10 feet right here. And we want to write an equation at position P, and the main other piece of important information is that the entire cycle takes 10 seconds. So we're going to start off here. I'll do blue. And we're going to go down. I don't have control over this thing sometimes. And we go back up. But that's close enough for grammar. We're just trying to get a feel for our position here. So, actually that's kind of ugly. Whatever. All right, moving on. So what we want to do is we want to write our equation. And again, where y is equal to a cosine b x minus c, but we don't have to worry about that, plus d. But since we're specifically told to write it as a function of p and a function of time in relation to p, we're going to have a p here, a cosine, and we're going to still have our b, but we can put a t, plus d. All right. That's a P. There we go. So let's go ahead and find our amplitude first. Amplitude is basically high, minus low, over 2. Okay? So it's going to be 18 over 10. 18 minus 10, silly me, which is 8 over 2, which is equal to 4. So my amplitude is 4. We want to find B. Okay? Well, our period, did I say phase? Is 10 seconds, right? Yeah, period is 10 seconds. So to solve for B, that's just 2 pi, or going around the circle once, divided by 10, which is equal to pi over 5. So that's going to go right there. Okay, our t is going to remain intact. To find the d, we're going to take amplitude plus low. So amplitude plus low is nothing more than 4 plus 10, which is equal to 14. That's going to go right there. So we have our function. P is equal to 4 cosine of pi over 5 x t. Didn't mean this to do that. T, that's a t. Ah, good grief, I'll erase it for you. T plus 14. All right. So let's say I wanted to find out the time, because this is going to be 10 seconds. That's my cycle. Say I wanted to find time at 4 seconds. Okay. I would plug 4 into here and calculate. You're going to get two different answers. Well, actually on this one, yeah, you will. God, that is a horrible picture. I don't like it. Okay. But all right. So it's got to go. It's got to go. I'm not going to redo this because I have challenges today. Let's see. Let's draw a little bit better picture. Still kind of bad. All right. So say time 3. I'm going to have a position right here. Okay. And that's what you'll be looking for. Okie dokie. Well, I am going to get this one posted and get on to maybe another one. I have challenges.